So these are just little plastic caps that we just have to penetrate and pull up because there's no other good way to pop them out. Probably mainly just for tamper evidence. So I got these 8 backed out. This is pretty much just our handle, but you do have to take it off to separate the top, it looks like. And we're in. So there we go. It is neat looking the way they have the ribbon. It does come out pretty neat, like a brick. Not to really compare, but since I do have an Ego pack, there's a 56 volt right beside it, we can see that we definitely have a more compact design here, but I think Ego did a better job with the cooling. They didn't mind making it wider. They tried to space the cells out for cooling as much as they could. Of course, this is a 2.5 amp hour, and as we saw in a previous video on the 5 amp hour repair for the Ego, it is of course twice the cells. Of course, there's this one. This one's also twice the cells. So this is more comparable to the 5 amp hour Ego. It's compact, but you know, the cells building up heat in heavy load situations and applications, I can see how it will build up more heat. But this particular pack, even though I bought it unknown of the issues, it doesn't have any cells that appear to overheat or have been overheated. If you're curious, there's the 18650 cell number of the Echo. Hopefully I've been saying that right, because I got Ego packs and this is the first Echo pack I've had apart. So as we take a closer look at this pack, we did notice it only lit up one light. We're only getting around 50 volts output, and this is a 58 volt pack is what Echo calls it. Now keep in mind it's the same 14 cells in series like the Ego pack, which is this of course is being, you know, 2 in parallel, and those 2 parallel being in series with the 14 others. So actually the 58 volt is not, you know, greater than the 56 volt rating of the Ego or other manufacturers. It's just what they determined to rate it, right? So they all 18650 cells so far, and it's all about the number that you have, of course, in series and what nominal value they're using. But some of them use different ratings. For example, we know the Ego, the 14, if you do it times 4 is exactly 56 volts. So they Ego uses 56 volts, so 4 volts per cell. And of course, if we take 58 and divide it by 14, Echo is coming up with, you know, like say 4.15. So they go to the high end of what you need to charge a 18650 cell, because usually 4.2 is about as high as you want to go. So they just try to push the limit on the rating a little bit. So as we get into this pack, I'm gonna try to turn it so we can see both sides here. So we got some this bank here is actually fully charged at 4.12. 4.12. So we definitely have some good cells in this pack, which we naturally know we will when we're reading close to 50 volts. It's only when a pack's starting to read really low that I get concerned that it might be, you know, all cells gone. And we're not getting anything across this bunch. I'm getting my 4.13, 4.12. Nothing across this bunch. And 4.14. So we do have a couple banks here that have pulled down, and that's just in that 7S section. Then if we flip it over to this side, just so you can see it a little better. Good. 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 And good. Good. It's good. All right, fairly well balanced and all good on the bottom. So all these cells are good, and at least there's a possibility of at least 2, if not 4 cells gone here. Probably is 4, because we probably have one bad cell on each section that is taking the other one to 0 volts. So I never hardly ever try to recover a cell that's gone to 0 volts. Me personally, I hadn't had the best of luck with even trying it. So yeah, the next to the last bank on what I'm calling the top here, where the terminals are, the next to the last, and then the third one in from the terminals get 0. So pretty happy with how many good cells we have here. It's just walking back and forth, right? Like you would think. We have a 2P. It's, in other words, probably 2,000 amp hour battery. I hadn't even looked the rating up, but just going by the rating that they put on the battery, 4 amp hour, must be 2,000 milliamp hour each 18650 cell. So you got a 2P, 2 in parallel, and then it's 14S, so 14 of those sets. So when you have one that's died down like that to 0, then that cuts the capacity and output of this pack down. And one thing I do want to do is ohm. You got to be careful ohming with voltage on there, but this is a high-end meter, and we do see that these cells not only read 0 volts, we see that they're showing like 1 ohm, just like a dead short here as well. That's the only reason our 50 volts is actually getting out. If these cells would have completely opened up, like the CID activation or something of that nature in the cell internally, then we would have been open and not getting hardly any voltage here to the terminals, to the battery output terminals. So we know right off that they must have been pretty low ohms or shorted. So we got at least one of these cells in the bunch that is almost a dead short, and you would definitely not want to put voltage across this for charging. Like even if you wanted the what they call boosting a pack, right, and putting 58 volts across it to see if you could get it up, well, you would definitely, once again, you would overcharge your good cells, because you got some in here in series reading 0 volts. So if you left 58 volts on here for a period of time, you would definitely be overvolting the pack by you minusing 8 volts. So you would actually put 8 volts distributed across the rest of the pack more, of course, than it should be. So the first thing I'm going to do is take one side of that red low. I'm going to pop this, one of the easiest to get to here. I'm going to pop that off and isolate that one cell. And that one is shorted. So they're both showing shorted, so they've been pulled down so low. And I kind of expected that to be the case. That's the only thing about these higher capacity packs when they put them in parallel then in series. If one of the cells goes out in parallel, of course, it's going to equalize and affect the other. Just naturally it's going to happen. So the high capacity packs are definitely nicer. They're a little heavier, but of course they last a lot longer. When you get these single packs, they cool better per like watt density, if you will. And then also, if one cell goes bad, it don't take another one down with it typically if you catch it in time and don't try to overcharge it. So that's one. Flip over to here, and we'll do this side here. Really a neat spot welding job that Echo does with the pack. That's got that battery there isolated, and I expect really the similar issue here. We're shorted, and if we go just anywhere on this whole top plate, I get this side, and yeah, we're still shorted. So it did, at least in my opinion, take out all 4 of these cells. That's still not a bad repair really. So even though this little ribbon cable here is neat, and we can just undo it by lifting up here, just pull this out. So that's neat, but unfortunately that is going to be difficult. I like to solder mine, and you definitely, on this side, we're definitely not going to be able to solder. That's actually on all the way around. So on this side, that's going to be the only catch with soldering. That is neat how they did the individual cell monitoring with the ribbon cable around. Makes it compact, I guess, but when you go to solder, it's actually nicer to have your wires out of your way there. So this one is a lot easier to repair, it looks like. So I'm actually going to put a little bit of flux on here, some liquid flux. See if I can just be gentle. Do not want to put a hole in a mylar. It is a little bit of mass there though. You don't want to it don't heat up as quick as I thought. I thought I could reduce the heat a lot, but if we see here's a good bit of mass. Alright, so that's got that removed. Now off camera I'll just keep on going all the way around to So a couple things worthy of mentioning. I definitely tried to keep the heat off the mylar, and so far so good. But you got to realize just how much mass you're heating up here if you stay on this tip. I had to pretty much take my soldering iron close to 700 degrees Fahrenheit, because I usually run mine around 690 or so. And I was going to try to do this a little bit lower temp, but I didn't want to melt into the mylar around on the ribbon. But with this being about each square having about the same amount of mass, it takes a little while to heat up. Another thing to keep in mind, I hadn't had any issues because I'm trying to be careful, but I'm going to take some packing tape and cover these up, because you got to think about it. Cells on the other side, you got difference in potential across these points, and you could let this go and come across and slap, and even though it would just be a small little arc, it could potentially mess up the ribbon trace, or actually would even blow the trace out. So just a thought there, might have to be really careful with that. This really is kind of a pain to swap cells out in. So as I got going through here, the rosin flux did help a little bit. Made this job a little easier, and down to the last two, that's plenty out of the way, but I think for now I'm going to go ahead take the last two off. It don't take that long, and then I'll just get the whole thing out of the way. I have marked it here, so if I do get some new cells and it's a week or so before I fool with it, I will remember how to put this back easy without having to think about it. So there we go, and looks like we might have a built-in thermistor there. That's neat. Right there close to the middle of the pack. As always, fooling with batteries, you just have to keep in mind what you're doing. There's no power disconnect on a cell, of course. So as I fold this back, and I got these two batteries here fully showing. You go to fool with this one, just remember here, you're definitely going to have a difference of potential across this pack. Probably above 20 volts here though. Yeah, see, we got almost 25 volts across these points with them in series. So you don't want to come across these, just keep that in mind. Whether you prime with a screwdriver, you just don't want to come across any two difference of potential in your battery pack. Sometimes it's even helpful to take an insulated item, just cover up this terminal so we can pry against if need be. And after getting this side loose, there's our BMS board. It's completely off. Take a little closer look at that board. We see our cell monitoring network coming up here. Yeah, because that's where our ribbon cable attaches, so where our negative comes across, our positive, and we see a fusible link here, a fuse. We also see a little programming header here for the microcontroller. It does have a conformal coating on it. You can see the shininess of it. So as you probably imagine watching the video, that this was going to be a difficult pack to get the cells out of. I did try to do it right. I was going to try to take even all the top on one side of loose, but I think this is like a glass embedded nylon mold here or something similar. It's really rigid. There's no give in it. Even taking all of them loose, you could tell right here that it wasn't much give in it. So unfortunately, you gotta decide just to part the whole pack out and just keep the good cells and keep the good BMS board for a later spare. Or you can decide to get a little creative since you don't have much to lose with those cells. And just so happen all four of these were 0 volts. So 0 volts and shorted, not open. Just keep in mind if these cells would have been open, then it could have been the CID could have opened up. In other words, the potential of power will still be in the cell. But these being shorter than 0 volts, there's not much danger in the cell right now. So what I decided to do was just take a good Stanley knife or razor blade and just score around just gently, just to make it weak. So I just hit these spots here a little bit to make them weak, and around here the best I could, these little tabs. And since these are already 0 volts, I simply took a deep well socket and just gently tapped until I got that to push through. And I felt like that might have been the best way to get them out. So this one we can see, I just pushed them through from this one was the negative side on these that were bad, and it just pushed out right here. So I'll be able to push my new cells in and solder them back in place, or spot weld them, whichever you prefer, right? So it's not pretty, but it works. Only after I got these out a more difficult way did I realize that if you go ahead and take this and this pad off, hopefully you can see that there's a screw in there that holds this part together, which you couldn't see with the batteries in there. So we got one here and we got one here, and of course this side I have them as well on the bottom. But you know, taking those out and taking these loose, it may give you enough room to wiggle these out. I didn't try that. I definitely tried the method of tapping them out, because it'll still have a holder lip on one side and I can solder them in and retain them. And since these were at 0 volts, but now I still have enough respect for lithium ion batteries that even shorter than 0 volts, these will definitely not be in my house overnight. But there we go, we got those 4 out. We just need 4 new cells, because all the rest of these check like they're in pretty good shape. So back now I have some Samsung 20Q or 2000 milliamp cells. I have these very balanced, as we can see here, 4.13, 4.13, 4.13, right at 4.13. And I've let these sit here for a few days to make sure they hold good. And you see we're real close to what our pack is already balanced out to be. So I think these will be a great fit. The only thing I've done to the pack since the last portion of the video, I did want to deburr these holes just a little. I actually used a unibit. You can do a file, a unibit, or maybe a little Dremel would. The unibit worked great just to clean that up. And we do know that the negative is going to go back into the back part of this battery. And man, that snapped in really nice. I don't know if you could actually hear that, but it's got a little ridge. It actually snaps in and holds real secure. So that's good, especially being able to solder it back. Do the same with these 2 cells. Alright, So next up, I'm going to bring over my 200 watt iron. That way we can just heat this up and put a little solder in there really quick without getting the sails really warm. I typically always use my 200 watt iron. On one of my previous videos, or more recent videos, I brought over this Avon iron to see how well it did, and it did a good job. It was pretty quick, but I did have a few comments from people that said, you know, I wouldn't leave it on there that long on them sails. So just to keep the negativity down, I'll do it the way I typically do with my 200 watt iron, and I'll make it really quick, cool it off fast, and we'll be good to go. So now on the battery pack, I'm going to put some RA flux, this rosin flux on here to help with the heat transfer. It also helps the surface. It'll help the solder stick to the surface and make it a lot easier to solder to, make it stick. It helps with the impurities. So I've already prepped the surface by, you can use a little emery cloth, or I chose a stainless steel brush, but cleaned it up, alcohol, flux. Now we'll go ahead with a 200 watt iron. We'll go ahead and heat the surface up enough for the rosin to be activated. So we see the flux, let it puddle up really nice. And it's cool to the touch just that quick. So as long as you do it quickly, we won't be heating up the sails at all here. They really won't heat up more than the higher level of operating temperature. So I wouldn't want to keep a soldering iron on them very long. But I've done this for years and have had no issues. I use lithium ions for all kind of things. And if this was a brand new or a better surface, and I wasn't putting some of the old ones back together as well, probably just tacking them, just spot welding probably been better. So that shows two of the minus or negative terminals of the battery. We'll do one positive. Then after we do a positive, I'll pause the video and just come back when I'm done. And it's just that easy. I'll just do the rest of these off camera to save time, and I'll be right back. So back now with the sails done. I've even made sure we had the plates tinned on the contact points. So all we have to do now is just solder the plates in place. I'm just going to keep going around till we complete. So that's got this side ready to go until I put the BMS board back on it. I hit all 6 of these spots. I'll have to hit these 4 with the board. But next I'll do this side, and this side will be complete. You just have to be mindful of the pack, even like trying to put something under here to bend these plates down. This way would be fine, but of course we went across this way, we would short. Would cause a short, so just gotta be mindful of your plates. Use something like a wooden swab or something non-conductive here to help you bend, because it does kind of look bad, but it's just because we done bent these plates around, trying to reuse them and save some money. And also I just put Kapton tape under here just to make sure on this positive side that we didn't come down too far. Now with all the sails connected back, before I actually solder on the BMS board, I want to just check the voltage across these sails. We are right at 58 volts. That's great. Very happy with that. Everything connected back together really good and solid. So next step is we'll be careful and put these strips back on. cells are connected, and we're getting our almost 58 volts to our terminals, and we see our board is powered. We're getting a flashing light due to this the chip on flex NTC, as well as the other cell monitoring is not put on yet. So off camera, I'm actually going to clean these up, probably get some solder wick. I'll get this soldering iron and just put it on lower wattage and just clean these up with some solder wick, and we'll be right back. Just taking the solder wick and going across, did a fantastic job cleaning these up. Just probably one thing worthy of mentioning is with anything similar to this, even circuit boards, you definitely don't want to do this and remove the iron, let it tack, and then rip off or peel off part of your trace or your pad there. Just keep that in mind. As like a circuit board, a regular circuit board trace, you just want to, when it starts flowing, just make sure you lift it while it's still flowing and wet. And I think that's got all the eyes opened up quite well. I do have to clean up these tabs as well, just going around with the desoldering pump and just trying to hit these tabs enough to melt the solder. We want to be careful and make sure we don't go across any of the plates and go across different potentials. So as just like as soldering before with the plates, we just got to make sure we stay and don't short across anything. Well, the rosin flux and the solder pump did a really good job here. That's exactly what we needed. Some of these tabs, I didn't even realize they had gotten bent or doubled over like that one. This one as well. I think it actually got at the factory after they put this on, they doubled it over. So that's good. We'll open it up and clean it up a little more, and then we'll get this on. Here we go, back now with the ribbon cable on the tabs for monitoring. For the individual cells. Oh yeah, that's got these all lined up. I'm going to go ahead and tack these on. Just try to put just enough heat. And yeah, you're supposed to heat up all surfaces together, but I'm definitely trying to stay on the tab more because the tab is a lot more heat sink on the tab. So I'm trying not to burn through this flex here. So I am trying to keep the tab heated only, and just let that heat migrate slowly to the flex. This is a first time for me with this on a battery pack. Neat enough manufacturing idea. I've been in manufacturing most of my career, so I understand this probably made it easy to manufacture, but I don't like using it I don't like repairing it with this. Just so happened that the Ego battery was a lot easier to actually work on a repair with. There we go. All right, what do you think? So we do know we have our almost 58 volts, and if we stay on our negative and come around here, this is kind of like the ego going around the BMS board, like what's coming around B1 to B7 and B8 to B14. If you saw that in the previous video repairing the ego board, this one is similar where we doing our individual cell monitoring across here. We can go across and add it up, or we can go from one to the other and see how balanced we are. All right at 4.1 volts. So that's good. Okay. So this, if we go here, that's all the way to 49 volts. And then one of these here, all right, there's our right at 54 volts. And then of course all the weight is going to be coming from this one, which is also this point on the board here. So there we go. There's almost 58 volts. We are getting a flashing LED. Even though the pack's almost fully charged. That might be a pack temperature indication. You might have to look at the RT1, the NTCs. So we know the light's blinking, like it's either temperature fault or pack fault. I tried holding the button down for 5 seconds and it didn't clear. But one thing I'm going to try, hopefully you can see this, on the microcontroller's configuration or programming header here, or where the header would be. We do see a clock, data, ground, 3.3 volt, and reset. I don't know the most about the microcontrollers, but one thing I'm going to do is I'm going to try to go from ground to reset. Instead of getting a little jumper, I'm going to do it with my actual meter leads here. Hopefully you can see that okay. We'll try to stay on the reset pad and go across to the ground pad and make sure that made connection there. Harder to do it staying out of the camera's view here, but ground and reset. And that's just going to reset the microcontroller. So we look, hey, look at there. It is full, and it really is full. But now our BMS is saying that it's full. So that's awesome, because I know that the BMS board was working fine before. It was just showing low, which it really was low because we had 4 bad cells in the pack. Just going to put the screws back on this BMS board. Everything's in good shape to put back together. I am going to put some more tape on here, as well as putting some tape here to keep this flush as I insert it back in the housing. Back now with some Kapton tape, keeping that out of the way. One thing to mention too before I put this back together, it looks like TTI actually makes the Echo battery. I probably need to research that and make sure that's true, but I see TTI on the board there. And what made me look for that, because I didn't even see it right off, even checking stuff on the board. But one thing I noticed is on some of the Ryobi packs, it's a very, very similar layout. The way that they do their little jumpers here, like that W2 jumper, W3, W1. It might be worth mentioning that I guess assuming how many cells they populate in the pack, they'll have different jumpers here. So for some reason W2's is not made here. It's not jumped across, but we have W3 and W1 is, so it's close to our test points as well. But just worthy of noting that hate to say it, I've always had issues with 40 volt Ryobi stuff because they pack so many cells in a tight spot, and I don't know how many people have trouble with these Echo packs. So there we go. We do have a Echo 58 volt lithium ion pack that is a 4.0 amp hour rebuilt. So I just thought it was worth doing on this video to see if I could get it working. I was very interested in the Echo pack. I did a good bit of work with the Ego 56 volt in previous videos, and just thought I would see what was in the Echo, look inside and see the differences, and see if we could get it going. If you like the video on this Echo battery pack, please like, share, and subscribe, and thanks for watching.